Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome to the subject of machine design 1. After going through the design of various screws and associated designs, now let us move to the design of those important aspects which are of course which play very major role in actual industry, and they are called design of bolted joints and welded joints. Let us begin with design of bolted joint first, and then we'll switch back to design of welded joints. Bolts we know as of now, and of course they are assembled with nuts, but when they are assembled they actually come in between some member. For example, a plate. If there is a plate and I have to fix it with the wall, of course there will be a plate. I'll dig into a hole, and through that hole I'll let the bolt pass. Now there are two ways. Either on other side also I can put the nut and then I fix this plate with another plate, or if this is a wall, this plate can be merged with the wall with the help of only one bolt. So that is how we need to understand how the bolted joints actually work in major aspects, and how their design and failure aspects come into picture. So there are basically three ways a bolted joint can be considered, and we are going to look at those three cases as three different ways. So let us start with it. So it's the design of bolted joints, design aspects. So let us begin with the case 1. I'll illustrate this case 1, very easy case. This is how the 3D diagrams look. There is a wall. To this wall there is a plate and some another member, like let us say a cantilever beam like this, is to be connected. Now of course there are different means of connection, but we will use say bolts. Now there is another word, or there is another member which is like bolt, and they are called rivets. Of course we'll look at these aspects afterwards. Let us look at the bolted joints first. So I can put 4 bolts in such a manner that this will be hinged or this will be fixed with the given wall. So if I look at the side view from this direction, I'll look it like this. This is the member, cantilever beam, let us say. This is the plate and this is the wall to which they are bolted. So number 1, 2 and 3, 4 actually express the bolts. Number 1, 2 over here, number 3, 4 over here. So we are showing only their center axis, right? So that is how the bolts are done. Now there are some important parameters. Force P is acting like this with some eccentric distance. Now distance I'll measure from the wall up to the force, action of force. And there are these two things like the distance of the tilting edge. Now guys, we need to understand that since the force is acting in such a manner that tilting, if it has to, this particular thing will happen about this particular edge, which is the lowermost edge. So we need to find out this tilting distance. So this tilting distance for this two will be L1 and L2, whereas the tilting distance for this two will be L3 and L4, and of course they will be measured from the bottommost end. So L3 and L4 are naturally greater than L1 and L2. So that is how this schematic is, and that is how the parameters are mentioned. So this case is the case where the load is acting perpendicular to the bolts or the axis of bolt. The load is acting perpendicular to the axis of bolt, but in the different plane as that of the bolts. If you can see, the load is acting in this plane, but the bolts are in different planes, right? So that is a case 1. Load perpendicular to axis of bolts in different planes. And that makes up my case number 1. So we are supposed to look at the failure mode also. So there are two ways this can fail. Of course, when we are bolting this particular thing, we are actually turning them. So when a turning comes into picture, there is direct shear. So it's the direct shear that comes into picture. And second thing is, when it is trying to, this particular thing tries to tilt off, they are actually being pulled out, or they are being tried to pulled out. So in that case, they will experience the tensile loading. So it's the tensile stress. So there are only two ways where they will fail predominantly, because the selection is in such a way that the different shear won't come into picture, or different kind of failure won't come into picture. There's another thing also, this direct shear, just because they are bolted in this manner, when this particular plate tries to come down, it will try to shear it off, and that's why I'm talking about direct shear thing, which actually comes into picture because of the rotation of the bolts. So these are two failure modes for this case. Let's look at the formulae which are associated. Design aspects of first case, of course, like I said, direct stress, direct shear stress. So let us say Fs is the shear force which is acting on one bolt. So if this is the total P which is given in the diagram, and N is the number of bolts, then Fs will be the shear force which is responsible, direct shear force responsible for shear of one bolt. In that case, if I need to find out shear stress, this will be my formula. Shear force on one bolt, divided by area of cross section of one bolt. Now this is the diameter of bolt, which is actually considered to be the core diameter of the bolt. We know that bolt is a kind of screw. I mean, it comes with the same analogy as that of screw. So there is a similarity between the screw nomenclature and bolt nomenclature, like core diameter, outer diameter, inner diameter, and so on. And that's why diameter can be considered as the core diameter. Then comes another aspect, that's called normal force acting on one bolt. Like guys, we have seen when this tries to tilt off, they will try to be pulled off. So this pulling happens in terms of normal force. So normal force on each of them will be different, right? And that depends upon not only the location but also the tilting location. Based on that logic, what we have seen is force in nth bolt should be equal to the total normal force into the length, or into the eccentricity of that particular bolt from the tilting edge. So this ln is nothing but L1, L2 and L3, L4. For bolt 3 and 4, the distance will be same. For bolt 1 and 2, the distance will be same. So in that case, if I can write it down for first bolt, it will be like F1 is equal to total normal force into L1. For F3, I can write it total normal force into L3. So that is how I can write down the expressions. In the case, if I go for the balance of the moments, I'll get this particular expression where total force will be given in terms of P, eccentricity, and the summation of square of all the lengths. So it becomes, if I elaborate it, it becomes P into E divided by, in case of 4 bolts, it will be L1 square plus L2 square plus L3 square plus L4 square. In case of more number of bolts, it will go on changing, provided that the pattern is maintained. So in that case, maximum force that acts on any of the bolt will be given by the total normal force into maximum length. So this, in our case, with our nomenclature, is possible only for third and fourth. So in our case, F max is equal to F into L3 or L4. Now, this particular aspect takes care of direct shear, and this thing takes care of normal stress, which in our case is tensile. So how to go about the stresses then? It's about the tensile stress. So it's very simple. The maximum force that is acting, the maximum tensile stress which is acting in the all the bolts or any one of the bolts will be given by the maximum force, maximum normal force acting in one of the bolts divided by its area of cross section. There comes the tau max thing and this thing. Now we know that it is under combined loading, and that's why we have to consider the maximum shear stress that's coming on the object, and the formula is very simple again. It's the square root of 4 times stress, and this thing comes out to be, now this is the maximum stress, which is of course principal. So it is sigma t divided by 2 plus of course using this we can find out these two stresses which are the maximum induced stresses in the given body. Accordingly we have to go for the selection. So it is tensile stress, combined stresses. Accordingly selection we have to do. Then now there is again two way. If the material is given, then we have to check its safety, then check its safety, or otherwise if no material is specified, select material with allowable stresses. So there is two way we can select the material after this. So this was the case number 1. Let's move to case number 2 quickly, where the bolt will be somewhat like this, or the thing will be somewhat like this. This will be the wall, or like unlike earlier case, this is how it will be in the same plane. The load and the wall will be almost in the same plane. This will be the eccentric distance. Now in this case, if I name these bolts like this 1, 2, 3 and 4, I must consider their geometric mean. So that geometric mean I'll name as G. So from that geometric mean, whatever distance this load acting P is there, it's called eccentric load in our case. So this is the case 2. Of course, load is again perpendicular to axis of bolts, but the plane in which P is acting, that plane is parallel to the plane of axis. So planes are parallel. So that's the case. Fine. Another thing is the distance or the direct distance between them will be called as radial distance. So it is R1, R2, R3 and R4. This is how the distances from the center point will be specified. So this is the important nomenclature as far as case number 2 is concerned. So let us move ahead with this case and let us look at the failure of this particular case. In that case, again direct shear will be in picture, and that will be nothing but total force divided by number of bolts. Now P is the acting load, right? There comes another aspect again, but in this case the actual force acting in one bolt will be given by the total force, now total normal force of course, into the radial distances. Now in such case the total normal force will be given by, so this is basically shear, of course direct shear, and this is basically tensile or normal stresses. So in such case, like earlier only, we have got the formula for total normal force is equal to the actual force into eccentricity divided by this particular expression. So in our case where there are 4 bolts equispaced, it becomes P into E divided by R1 square plus R2 square plus R3 square plus R4 square. So in that case, the resultant force acting on these bolts will be because of the shear force and because of the normal force or tensile force, we'll call it. So in that case, it will be a combined loading if of course this particular expression derivation is not a part of this thing. So it's an empirical relation given, that is it is the, let me make the correction. So it is ft square plus fs square plus 2 times ft fs cos theta, whereas this theta is the angle between ft and fs. So if the data is given accordingly, we can find out the theta and then we can proceed. The last thing here is we have to find out the shear that is actually acting on this. So that will be the maximum resultant force, like we have seen in the last slide, divided by area of cross section. So based on this, we are going to select the material. So that is the case number 2. And let us move on to case number 3, which is our last case, where the location of P force, the applied force will be in the same direction as that of the bolts are acting. So nomenclature for this remains the same. These are the lengths L1, L2, and these are the lengths L3, L4, because these are bolts 3 and 4 here. The only change here is P is acting in the same direction as that of the axis of bolts are. So P parallel to axis of bolts. So that is the case number 3. Now in this case, eccentricity will be defined in terms of the mean distance between L1, L2 and L3, L4. So that is how the eccentricity will be defined. So that is the diagram of case number 3. Let's look at the failure quickly. Now there are 2 ways failure will happen. Failure will happen because of primary tensile force that is acting, and that will be simply P divided by N, because this force, since it is acting in the same direction as that of bolts, the actual force will be divided into 4 parts, and that's why it is called primary force. But there comes another aspect. Because of this, the tilting may also happen, because there is some eccentricity as far as the geometry or the geometric mean is concerned of length 1 2 and length 3 4, and that's why the tilting may also happen, and that brings in the secondary tensile stresses. And for that secondary tensile stresses, the formula is very simple. It is the actual F, the actual normal F, that is because of tilting, into maximum length. So in our case, the maximum length is either L3 or L4. To find out F, the expression is this: it will be P into E divided by the summation of length square. So in our case, where there are 4 bolts, it becomes P into E divided by L1 square plus L2 square plus L3 square plus L4 square. So that is how we can find out value F. After substituting this value F into this equation, we'll get secondary tensile stresses or secondary tensile forces which are acting in this particular case. Of course, resultant will be combination of these two, the direct one and the one which is because of tilting. And that's why this is the expression resultant force. We are discussing about the resultant force that will act on the bolts because of this kind of case. So that will be the primary tensile force and the secondary tensile force. Let me quickly remind you that primary tensile force is just because of the same direction of actual force acting in the direction of the bolts. So that's the primary one, and secondary one is because of the tilting effect that's happening because of the eccentricity. So the tensile stress in this case, which is the only possibility in this case, will be given by the resultant force divided by area of cross section. Of course, if we have to consider the direct stress also or the direct shear stress also, in that case the formula remains the same, which is equal to the shear force divided by the area of cross section. But in this case, if we are not considering the weight of the plate, so direct shear force won't come into picture. But if we, because the force is in the same direction, shear force will not be there because of the force P. So this is how the tensile stress will be obtained, and based on which material can be selected. Selection will be done in the same way we have been doing. So that is what the design of bolted joint is all about. So let me quickly summarize. When bolts or rivets are used for the joints, we generally drill. Of course, there are many ways, but we in our case we are considering 3 basic cases, where in first case the bolts will be attached with the walls, but the force will be perpendicular to the axis of the bolts. Also, that will be at certain eccentricity. Because of this, there will be two prominent stresses induced. One will be the direct shear stress, and second will be the um, tensile stress induced because of the eccentricity or the tilting that's happening. Then second case we have seen where the bolts will be bolted in the same way and the force will be perpendicular. So in the second case, the bolts will be drilled in such manner and the force P will be acting in the same way. The only difference being, in this case, both the direction of force P and bolts are completely in different directions. The only thing is the eccentric distance of the wall and force P will be the same. So in such case, there will be direct shear, of course, because of force. Also, there will be the equivalent normal stresses, and because of which the failure may occur. The last case which we have seen, where the direction of bolts will be same and the force will be in the same direction of the bolts, and that's why the failure will occur because of the primary tensile stress, which is because of the division of this one force into 4 or number of bolts and the tilting effect that's happening. That is how the design aspects are concerned and the formulae related are given. In the next lecture, we are going to look at the numerical which is based on the design of bolt joints. Thank you so much for watching this video. If you like this video, please subscribe to Ekeeda. Thank you.